Now let's turn our attention to the stability and condition of a mathematical problem. The condition of a mathematical problem relates to the sensitivity of a function to the change in its input parameters. So for example, if we change a value of the input parameter and the function value changes significantly, it means that that function is sensitive to that parameter. So we generally say that a computation is numerically unstable if the uncertainty of the input values is grossly magnified by the numerical method. So we can explore this again with the first order Taylor series expansion, because that sentence was a mouthful. So we can say that f of x can be approximated by the f of x tilde, so the approximate value at x tilde, multiplied by the derivative and our step size at x tilde. Remember, we're working at the approximate location here. And we can also then look at, we can rearrange this and look at the relative error, so we divide by f of x, and that turns out to be, gives us a nice formulation. So we can say that the error, this is this difference between f of x and f of x tilde, divided by the function value. So now we're normalizing it, we're looking at the relative error. It can be approximated with the first derivative of at x tilde multiplied by our step size divided by the function value at x tilde. Now, we also know that there's an error in x. So the relative error of x is just the difference between x and x tilde divided by x tilde. And if we take the ratio of these two numbers, we call this the condition number. And that is a measure of the extent to which the uncertainty in x is magnified by f of x. In other words, the condition number c of n is equal to the approximate value of x multiplied by the first derivative at x tilde divided by the function value at x tilde. Now, make sure you know how this number is configured. So use what you learned about the Taylor series to try and get to the same number. And you need to know what the ratio between which relative errors and the denominator actually means. So we can explore this quantitatively by saying that if the condition number is greater than 1, then our relative error is amplified. Whereas if it is less than 1, then it's been attenuated. Now, if the condition number is significantly large, we refer to that function as being ill-conditioned. So let's explore this again with another example.